So, Jai Hind everyone, I am Dr. Karunesh Srivastava from Ajay Kumar Garg Engineering College, Ghaziabad. In this lecture, I am going to discuss about the time domain analysis, which is related to the subject control system of third year 6th sem. So, first of all, I will discuss what is time response analysis. The time domain analysis refers to the analysis in which system performs with respect to the time. It is used to evaluate the state and output responses with respect to time. The time response of the control system usually divided into the two parts, that is transient response and steady state response. So, what is the transient analysis? Transient analysis is defined as a part of the time response that goes to 0 as time becomes very large. And steady state analysis, it is the part of the total response that remains after transient has died out. It means after a particular time, after a particular time when the input is approaching to the output. It deals with the estimation of a state of error between input and output. In case of a steady state analysis, we will find the steady state error between input and output. In case of transient analysis, we will find the time response of the system. Before going to the time response or before discussing the time response of the system, we should know the standard test inputs. In most of the cases, the input signal to a control system are well known prior to the design of the control system. So, hence to analyze the performance of a control system, it is excited with the standard test signals. In general, control system design specifications are also based on the response of the system to such test signals. So, standard test signals include unit impulse, unit step, ramp signal, parabolic signal and sinusoidal signals. These inputs are chosen because they capture many of the possible variations that can occur in any arbitrary input signal. So, what are the input types? I have already told that unit impulse signal, unit step signals. Unit impulse signals are mathematically defined as minus infinite to infinite delta t is equal to 1, and the Laplace transform of this unit impulse signal is 1. So, what is unit impulse signal? It is the area under the curve for this signal is unity, not the amplitude. So, unit step signal is a signal that switches to 1 at a time instant and stays there indefinitely. Mathematically, you can say that xt is equal to 1 for t is greater than 0 and 0 for t is less than 0. It means xt is equal to 1 for every t is greater than 0 and 0 for every t is less than 0. It means signal is not defined at t is equal to 0, it is defined for t is greater than 0 and t is less than 0. So, there is an abrupt discontinuity at t is equal to 0 and the amplitude at t is equal to 0 is 1 by 2. You can take for defining the abrupt discontinuity, I have to discuss in another, I have to take another lecture for discussing this. Laplace transform of this unit step signal is 1 by s. Now, ramp signal, mathematically xt is equal to 80 for t is greater than or equal to 0 and 0 for t is less than 0. So, Laplace transform of this is a by s square. Parabolic signal xt is equal to 80 square by 2 for every t is greater than or equal to 0 and 0 for every t is less than 0. So, Laplace transform of this is a by s cube. Now, coming to the type and order of the system. So, every transfer function representing the control system has certain type and order. The steady state analysis depends on the type of the system. So, how will you define the type and order of the system? I will discuss in the next slide. The type of the system is obtained from the open loop transfer function, and the number of open loop poles occurring at origin determines the types of the system. Suppose open loop transfer function GSHS is equal to S plus Z1 S plus Z2 upon S की power n S plus P1 S plus P2. If n is equal to 0, or you can say the power of S will define the order of the define the type of the system. If n is equal to 0, it means this is type 0 system. If n is equal to 1, it means this is type 1 system. If n is equal to 2, this is type 2 system. So the number of poles occurring at origin will define the type of the system. So what you have to see, you have to just find you have to just see the open loop transfer function. In open loop transfer function, how many poles are occurring at origin? Number of poles occurring at origin will define the type of the system. Now coming to the, and this steady state analysis depends on the type of the system. The transient analysis depends on the order of the system. The order of the system is obtained from the closed loop transfer function, that is GS upon 1 plus GSHS, or you can say the characteristic equation, the power in this characteristic, power of S in the characteristic equation will determine the order of the system. I have already told you that the value of n in the denominator denotes the number of poles. The system with n poles at origin is called the type n system. Now let us take an example. Here the GS you have to find the order of the following unity feedback system. So here GS is equal to 10 S plus 2 upon S square S plus 5 is given to you, and it is saying that the HS is equal to 1. You have to find the value of, you have to find the order of the system. For finding the order of the system, you will write characteristic equation 1 plus GSHS. What will be the value of 1 plus GSHS? You will get here S cube plus 5S square plus 10S plus 2. The highest power of S will determine the order of the system. So here the highest power of S is 3. So the 3 is the type of the, 3 is the order of the system. Similarly, you can find the type of the system. The number of poles occurring at origin is 2. So this is the type 2 system, and order for this system is 3. Now coming to the transient response analysis. So in transient response analysis, we will consider this the transfer function, and the zero order system will be, we can find the zero order system using this equation, or you can write directly x naught by xis is equal to b naught by a naught, where x naught is the output and xi is the input. Here x naught by xi is equal to k, which is a constant. So here you can say that if I am designing a zero order system, then this is used, or this is used in case of sensors and transducers. So and we cannot analyze, we cannot find the time response, and we cannot find the time response analysis for such type of system whose transfer function is constant, or you can say that is a zero order system. So in case of zero order system, we cannot perform the time response analysis, and because the input output characteristic of such type of system is linear. Now coming to this first order system, we can define this first order system like this: x naught x upon xis is equal to b naught upon a1s plus a naught. So here you can write like this, by taking this a naught common, you can write k by 1 plus ts, where k is equal to gain b naught by a naught. So this first order system, we can find the time response analysis, we can do the transient analysis for this first order system. So we have find this, the first order system is this: x naught upon xis is k upon 1 plus ts. So what is the transfer function? Transfer function is 1 by 1 plus ts. So here the impulse response will be like this. Impulse response means I am giving the input to the system. Here the input is Rs and output is Ys. Input given to the system is impulse signal. The Laplace transform of the impulse signal is 1. I have already told you in the previous slides. And what will be the value of Ys? Ys will be equal to 1 by St. So we can find the value of Yt or response of the system. Yt is equal to L inverse, Laplace inverse of Ys. This is nothing but 1 by t e की power minus t by tau. So this response is, time response is exponential in nature, or you can say decaying in nature. At t is equal to 0, it is approaching the value of 1 by t, because this factor will become 1 and you will get 1 by tau, or you can say this is 1 by t. And as well as time increases, at t is equal to t, you will get here at t is equal to tau. At t is equal to tau, it will become 1 by t e inverse. 1 by t e inverse is nothing but 0.37 by 1 by t. So it is at t is equal to infinite, you will get here t is equal to infinite, e की power minus infinite will become 0 and the whole factor will become 0. So this time response will approach to 0 at t is equal to infinite. Similarly, in case of a step response, we will consider the step signal as an input. So step signal as an input, so what will be the step response? Rs will be equal to 1 by s. Laplace transform of a step input is 1 by s. So what will be the output of output Ys? Output Ys is nothing but the system gain multiplied by the input. Ys by Rs is nothing but 1 by 1 plus s tau. So I will put here 1 by Rs is equal to 1 by s. 1 by s 1 plus s tau. So after solving this by using the partial fraction, I will get here 1 by s minus tau by s 1 plus s tau. By taking the inverse Laplace of this, what will I get? I will get Yt is equal to 1 minus, you can take common tau here, it will become s plus 1 by tau. Tau will be cancelled out from here, so you will get here 1 by 1 s plus 1 by tau. So you will get here 1 minus e की power minus t by tau. What will be the steady state error? The output for this system is, the desired output is 1. So what will be the difference between input and output? Input is a step signal, output is 1 minus e की power minus t by tau. So if I find the steady state error, output minus input, you will get here e की power minus t by minus e की power minus t by tau, and the steady state and TSS at t is equal to 1. So this is the step response of the first order system. In this case, you have seen the time response of the first order system. So now coming to the standard form of the second order system. What is the standard form of the second order system? This is the standard transfer function for the second order system, for which the forward gain of the forward path is omega n square upon s plus 2 zeta omega n. By giving the unity feedback to this system, I will get the standard form of the second order system. So what will you get? Ys by Rs is equal to omega n square upon s square plus 2 zeta omega ns plus omega n square, where omega n is the system natural frequency and zeta is the system damping ratio. This now I am going to do the analysis. I am going to find the value, find the system parameters. So basically there are three parameters, that is system damping ratio. It is a dimensionless quantity which describing the decay of oscillation during a transient response, and it is the ratio of the actual damping to the critical damping of the system. What is the system natural frequency? It is the angular frequency at which the system oscillates, tend to oscillate in the absence of the damping force. What is the damping frequency? What the system damped frequency? It is the angular frequency at which the system tends to oscillate in the presence of the damping force. That is omega d is equal to omega n under root 1 minus zeta square. Now coming to the response of the second order system. So response of the second order system mainly depends on the damping ratio zeta. For any test input, the response of the second order system can be studied in 4 cases depending on the damping effect created by the value of zeta. So for zeta is greater than 0, this is over damped system. Zeta is equal to 1, critically damped system. Zeta lies between 0 and 1, this is the under damped system, and for zeta is equal to 0, this is the undamped system. So I will consider each case one by one with their responses. impulse response of the second order system. Input is impulse response, that is RS is equal to 1, and for zeta is equal to 1, this is undamped case. If I put zeta is equal to 0, you will get here omega n square upon s square plus omega n square. So what will be the value of yt? Yt will be equal to omega n sine omega n t. In case of underdamped system, zeta is in between 0 and 1. So the ys will be equal to omega n square, ys is equal to omega n square upon s square plus 2 zeta omega ns plus omega n square. So by putting the value of underdamped system, by putting the value of rs is equal to 1, we have to calculate the value of yt by finding the Laplace inverse of this equation. By finding the value of Laplace equation, inverse Laplace of this equation, you will get yt is equal to omega n upon under root 1 minus zeta square e की power minus zeta omega nt sine omega dt. These are the responses. This is the impulse response and this is the underdamped response in case of impulse input. For zeta is equal to 1, that is critically damped case, you will get here omega n square s square plus 2 omega ns plus omega n square. So this is omega n square s plus omega n square. So yt is equal to omega n square t e की power minus omega n t. You will get here, you will get this by taking the inverse Laplace of this equation. For zeta is greater than 1, this is the overdamped system. Ys is equal to omega n square upon s square plus 2 zeta omega ns plus omega n square. For this, zeta is greater than 1, again I have to find the value of this, I have to find the Laplace inverse of this equation, and by taking this yt will be equal to this. So these are the responses in case of zeta is equal to critically damped case and in case of overdamped case. Now coming to the step response. In case of step response, Rs is equal to 1 by s, and I will consider each cases of each case for the value of zeta. So ys is equal to omega n square upon s square plus 2 zeta omega ns plus omega n square. This is the value of ys. So for zeta is equal to 0, I will put zeta is equal to 0, I will get here omega n square upon s square plus omega n square. By using the partial fraction, I will get here 1 by s minus s upon s square plus omega n square. So for finding the value of yt, I have to take the inverse Laplace of this. So what will I get? Yt is equal to 1 minus cos omega nt. Now taking the case of underdamped system, for which the zeta is lying between 0 and 1. So in this case you can find omega n square upon s square plus 2 zeta omega ns plus omega n square. First of all, what will I do? I will convert this into this form, omega, by using the partial fraction. By doing the partial fraction, what will I do? I will get the value of for such type of system or for such type of equations, you can use the partial fraction a by s plus bs plus c upon s square plus 2 zeta omega ns plus omega n square. So by using this partial fraction, we can find the value of a, b and c, and you can put, after putting the value of a, b and c, you will get 1 by s minus s plus 2 zeta omega ns upon s square plus 2 zeta omega ns plus omega n square. After solving this, 1 by s minus s plus zeta omega n upon this minus zeta omega n upon this. What I am going to do the perfect square of this denominator. I am going to make this perfect square, this denominator omega n square. For making this perfect square, what I have to do? I have to add zeta square omega n square and subtract the zeta square omega n square. So what will I get here? 2 zeta omega ns plus omega n square plus zeta square omega n square minus zeta square omega n square. So by using this is nothing but s plus zeta omega n square, and this is, by taking the here omega n square common, you can write here 1 minus zeta square. This is nothing but omega d square. So I can write here s plus zeta omega n square plus omega d square. and you can get 1 by s minus s plus zeta omega n upon s plus zeta omega n whole square plus omega d square. Similarly, you can get here minus zeta omega n upon s plus zeta omega n square plus omega d square. Now you can take the inverse Laplace of this. So what will be the value of 1 by s? 1 by s is nothing but 1. Here you can see here s plus a upon s plus a ka whole square plus b square. So this is nothing but e ki power minus at cos bt. So here b is omega d, a is zeta omega n. So inverse Laplace of this will be e ki power minus zeta omega n t cos omega dt. Now here the factor is zeta omega n. What will I do? I will multiply it with 1 minus zeta under root 1 minus zeta square for getting this factor here. So this factor is nothing but omega d. Omega d is nothing but under root omega n under root 1 minus zeta square. Omega n under root 1 minus zeta square. So you can write here zeta upon under root 1 minus zeta square, and by using this omega d square upon s plus zeta omega d upon s plus zeta omega n square plus omega d square. What will be the inverse Laplace of that? Omega d upon s plus zeta omega n square plus omega d square. This will be equal to e ki power minus zeta omega n t sin omega dt. After solving this, you will get yt is equal to 1 minus e ki power minus zeta omega n t under root 1 minus zeta square. I have considered here 1 minus zeta square is nothing but sin theta. So if sin theta is equal to under root 1 minus zeta square, then cos theta will be equal to zeta. So I can replace this under root 1 minus zeta square by sin theta and zeta by cos theta. So this equation will become 1 minus e ki power minus zeta omega n t upon under root 1 minus zeta square sin theta cos omega dt plus cos theta sin omega dt. Now you can write this equation as a sin a plus b. This is nothing but sin omega dt plus theta, and so this equation will become yt is equal to 1 minus e ki power minus zeta omega n t under root 1 minus zeta square sin omega dt plus theta. So this is the solution of second order system with impulse with step response. So this is all about for today. I will discuss the next topic, steady state error, in the next.